Welcome to the Explainer. I want you to picture just for a second a highly stressed manager at a wildly busy restaurant. They're taking orders, directing the kitchen staff, seating guests, dealing with complaints, and they're doing all of this seemingly at the exact same time. Well, believe it or not, that is exactly what your computer's operating system is doing every single second. Today, we're going to look right under the hood to figure out how an operating system perfectly juggles thousands of simultaneous tasks without just completely collapsing into chaos.
So to kick off our masterclass today, here's a fascinating real-world paradox for you to chew on. Imagine your computer has just one single CPU core. Yet, right now, you probably have a web browser open with 20 tabs, maybe Spotify is playing in the background, your word processor is waiting for you to type, and your files are quietly syncing to the cloud. It's all happening at once. But if a CPU core can technically only execute one instruction at a time, how on earth are you running 50 apps simultaneously? Well, the answer lies in the hidden, lightning-fast mechanics of multitasking.
Okay, let's dive into this. To really understand how multitasking works, we first have to clarify the difference between a program and a process. On the left, you've got a passive program. Think of it like a recipe book just sitting on a shelf. It's honestly just a file resting on your hard drive. But an active process, over on the right, that's the actual cooking happening in the kitchen. The second you double-click an executable file, the OS loads it into memory, and boom, it becomes the process. It's not just static code anymore. It now has a stack for temporary data like function parameters, a data section for your global variables, and a heap for memory that gets dynamically allocated while it runs. So one passive program, like your text editor, can actually spawn multiple active processes if you open up a few different windows.
All right, Section 1, Anatomy of OS Juggling. Let's see how the OS actually manages this chaos.
So how exactly does the OS keep track of all these active kitchens at the same time? Well, every process goes through a really strict life cycle, constantly bouncing between 5 fundamental states. When it's first created, it's in the new state. From there, it shifts to ready, which just means it's sitting around waiting to be assigned to the processor. Once the OS gives it the green light, it enters the running state, and this is where instructions are actually getting executed. But, it rarely stays there for long. If it needs to wait for something, like you taking forever to type on the keyboard, or maybe a file downloading, it moves over to the waiting state so it can get out of the CPU's way. Once that's done, it loops right back to ready. And finally, when the whole task is finished, it reaches the terminated state. This hyperactive, constant shifting is what creates that seamless illusion of simultaneous execution for us. But wait, here's the million-dollar question. How does the OS remember exactly where a process left off when it gets interrupted? It uses something called the Process Control Block, or PCB for short. You can think of the PCB as a super detailed ID badge mixed with a clipboard for each process. It holds the process's current state, its unique ID number, and, this is absolutely crucial, the program counter. That counter marks the exact location of the very next instruction it needs to execute. The PCB also keeps a snapshot of all the CPU registers and memory limits. Without this clipboard, the OS would literally lose its place the split second it looked away from a task.
Moving on to Section 2, the cost of context switching. Let's talk about the price of all this juggling.
Swapping these ID badges back and forth requires an intense balancing act for the CPU, which we call a context switch. To put this in perspective, imagine you're deeply engrossed in a complex video game, fighting a boss, and suddenly your phone rings. To answer it, you have to pause the game, carefully note your exact health, coordinates, and inventory so you don't lose any progress. That is step 1, saving the state into the old PCB. Then, you pick up the phone and recall where your conversation with your friend left off. That's step 2, loading the state from the new PCB. Only after all that can you actually begin talking, which is step 3, executing the new process.
Now this brings us to a highly counterintuitive insight. Context switching is pure overhead. Take a close look at the timeline here. While the OS is busy saving the state into PCB 0 and then painstakingly reloading the state from PCB 1, the CPU is completely idle. The system is doing absolutely zero useful work for your actual applications during that switch. And this is a massive engineering constraint. The more complex the operating system and the fatter the PCB, the longer that context switch takes. If an OS switches processes too frantically, it spends all its time just managing the switches, instead of, actually getting your work done.
That brings us to Section 3, and I absolutely love the terminology here: birth, death, and zombies.
So, now that we know how processes run and pause, how are they actually born and destroyed? The OS world uses some unexpectedly dramatic terms for this. When processes are created, they form a strict parent-child relationship. Usually, when a child process runs its very last statement, it politely asks the OS to delete it using the exit system call. But it can't just vanish into thin air. It has to return its final status data to its parent. The parent then collects this data using the wait system call. But what if the parent is super busy and hasn't invoked wait yet? Well, the child process officially becomes a zombie. It's dead, but its remnants are still lingering out there in the system. And it gets wilder. If a parent process terminates entirely without ever waiting for its children, those surviving children are officially labeled orphan processes.
Now, what's really interesting about this slide is that every single process on your computer is part of one massive family tree. In Unix environments, a parent uses the fork system call to spawn a child and then exec to load a brand new program into that child's memory space. But if you trace every single branch of this family tree all the way up to the very top, they all originate from one ultimate ancestor, the root init process. And that process always has a process identifier, or PID, of 1.
Because of this strict family tree structure, the OS sometimes has to employ a brutal but totally necessary efficiency measure called cascading termination. See, some operating systems flat out refuse to allow a child process to exist if its parent has terminated. So if a parent process dies or crashes, the OS aggressively steps in and terminates all of its children. And then it terminates all of their children and their grandchildren and so on down the line. It literally wipes out entire branches of the process tree just to prevent the system from getting overrun by uncontrolled orphan processes eating up precious resources. Section 4. Breaking isolation, or how processes actually talk to each other.
Up to this point, we've talked about processes as these strictly isolated little boxes. But if they're totally walled off, how do they collaborate to build massive, complex apps like the web browser you're using right now? They do it through inter-process communication, or IPC. There are two dominant models for this, and they both come with major trade-offs. First, you have shared memory. This is blazing fast because processes are reading and writing to the exact same block of memory. The catch? It requires incredibly complex manual synchronization. If two processes try to write to the same spot at the exact same millisecond, your data gets completely corrupted. The second model is message passing. It's a bit slower, sure, but it's much simpler to program since you aren't sharing an address space. Plus, it's the absolute ideal model for distributed networks, kind of like sending a chat message over the internet.
Let's look at the physical architecture here, because the differences are stark. On the left, with shared memory, those strict OS boundaries are deliberately torn down. The OS sets up the shared region, but after that, it completely steps out of the way. The processes are on their own to manage synchronization. But on the right, with message passing, the OS kernel stays heavily involved. It essentially acts as a secure post office queue. Process A sends a message directly to the kernel, and Process B retrieves it from the kernel. It's highly organized and safe, but of course, it involves that pesky context switching overhead we talked about earlier. When we build message passing systems, they can use either direct or indirect communication. In direct communication, the sender has to explicitly name the receiver. It's a strict one-to-one link. But indirect communication, that uses shared mailboxes with unique IDs. And this is where it turns into a really fun logical puzzle. Think about it. If processes P1, P2, and P3 all share mailbox A, and P1 drops a message in, who gets it? The OS has to decide. It might force a rule where only two processes can link at a time, or it might just randomly pick a receiver and notify the sender. Managing that kind of chaos is an incredible feat of engineering.
All right, our final section, Section 5, Pipes and Future Implications. Let's look at some real-world IPC.
Let's talk about a real-world application that developers rely on every single day. Standard communication often uses what we call ordinary pipes. You can visually picture this as a literal physical pipe acting as a one-way street. It operates in a strict producer-consumer style. The parent process pushes data into one end of the pipe, and the child process reads that data out of the other end. But because it's strictly unidirectional, data only flows one way, it absolutely requires that rigid parent-child relationship to work. On Windows systems, you'll sometimes hear these called anonymous pipes. But as you can imagine, developers eventually needed something way more flexible. Enter named pipes. Named pipes completely shatter the limitations of ordinary pipes. First off, they allow for bidirectional communication, meaning data can flow back and forth. But here is the real game changer. No parent-child relationship is required whatsoever. Entirely unrelated processes can just hook into a named pipe and talk to each other freely. That makes them immensely powerful for building complex, modular software, whether you're on a Unix machine or a Windows system. So, we've covered a lot of ground today. We've explored how an OS juggles active processes,
The hidden delays of context switching, the dramatics of zombie and orphan processes, and the tightropes of inter-process communication. But I want to leave you with a thought-provoking takeaway. Everything we just discussed works brilliantly for a standard laptop with a handful of CPU cores. But as we transition into an era of massive supercomputers with tens of thousands of cores and globally distributed server networks that try to act like a single machine, how are these communication models going to evolve? Managing the ultimate chaos at that massive scale is the next great frontier of computer science. Thank you for joining me for this deep dive on the Explainer. Keep learning and keep questioning how the invisible systems all around us actually work. Catch you next time.